Hi there, my name is Turk, and today I'll be talking about my experiment I performed, which was a synthesis of isopentyl acetate, also commonly known as banana oil. Esters are covalently synthesized from carboxylic acid and alcohol in the presence of an acid catalyst. And when performing a procedure, it is very important that you perform all parts of the procedure, not to skip any steps, because altering the procedure could, in the end, alter your results. Alright, so just a little preview on what I did was isopentyl acetate was synthesized through an equilibrium reaction between acetic acid, isopentyl alcohol, and the presence of H2NO4, which is also commonly known as our catalyst. It is synthesized with a microwave reactor, and we confirmed that isopentyl acetate was produced with our HNMR data. So how a microwave reactor works is you set on the computer, you place your sample in the microwave reactor, and then with the computer you enter in a specific temperature you want your solution heated up to, the allotted time you want it to be heated at that temperature, and then once the time has allotted, the temperature you would like your sample to be cooled down to. And why a microwave reactor is so efficient is because it heats the core of the sample from inside to out, which helps save time and money in the heating process. And then it's cooled down with an air compressor. So HNMR will help determine that we did indeed produce isopentyl acetate, because HNMR tells us a lot about the hydrogens on the molecule, and since we know the structure of this molecule, it'll be easy to see which hydrogens are which peaks. So what HNMR tells us is, first off, how many different hydrogens, which is the amount of peaks in our molecule. Two, what those hydrogens are next to, as in electronegative elements, as in oxygen, fluorine, sulfur, things like that. Thirdly, it tells us the splitting of hydrogens, which means what hydrogens are next to other hydrogens. Are they close enough where they can have an effect on each other? And lastly, the integration of those hydrogens, which is how many hydrogens is in each peak that we see on our graph. And how this works is a magnet lines up protons of our sample, and then it's hit with radio waves to knock those protons out of alignment, and as they come back up, their frequency is read, which in each different type of hydrogen gives off a different frequency depending on their splitting and what they're next to. So what I did in my procedure was I placed 4 milliliters of acetic acid, 2.8 milliliters of isopentyl alcohol, 20 drops of sulfuric acid, which was our catalyst, 2 grams of silica beads, which was used in the end to remove all the water from our sample, so all we had in the end was isopentyl acetate, and I placed them all in a 35 milliliter reaction vessel. And what I did with that is I put that in the microwave reactor, and I set the computer to 130 degrees Celsius for 15 minutes. And then once the 15 minutes had allotted, I set the temperature for it to be cooled down to 50 degrees Celsius. And then once our sample ran through the microwave reactor and cooled down, we ran it through the HNMR. And what my data showed me. When I first looked at my data, I could tell that something went wrong in my procedure. My graph showed that I had 5 different peaks, which means there are 5 different types of hydrogens in my molecule, which I knew was wrong instantly because there was only 4 different types of hydrogens in this molecule. So our first peak that we saw was integrated for 6 hydrogens, and it was a doublet, meaning that there were 6 hydrogens that were the same, and those 6 hydrogens were talking to one other hydrogen. They were close enough to one hydrogen that they would have effect on each other, which was normal. When looking at the structure, you could see that. The second peak we saw was integrated for 3 hydrogens, and this was a multiplet. And what this means is that there was 1 hydrogen and 2 other hydrogens that were so similar in structure that they were considered to be all one type, even though they weren't bonded in the same place. And the third peak we saw was also integrated for 6 hydrogen, and it was a singlet. And I knew this peak was wrong right when I looked at it because there was only one singlet hydrogens on this molecule, and it was only integrated for 3, and we saw 6. So the fourth peak that we saw was integrated for 2 hydrogens, and it was a triplet. And this we saw in our molecule because there was 2 hydrogens that were next to 2 other hydrogens, which would make it a triplet, so that made sense. And then the last one, which confirmed that our data was wrong and something was left over in our solution, was a peak at about 8 ppm, and it was 1 hydrogen, and it was very deshielded, and it was a singlet, meaning this showed me that there was an OH left in our sample. And this led me to the conclusion that there was leftover acetic acid in my sample. So how did this acetic acid get there? Well, when I was doing my procedure, I missed the step in removing the acetic acid. I was supposed to wash my sample after it ran through the microwave reactor with 10% sodium bicarbonate, and this would help neutralize the acetic acid, and then the neutralized acetic acid would essentially be water and soaked up by the silica beads. Alright, so I found that I did indeed produce the isopentyl acetate, but I skipped a step in removing the leftover acetic acid, which led to my data being skewed. And missing a step in the procedure can alter your results, but these results are not useless. Determining what mistakes you made from the results can help you in the future to not make these results, and it's also a part of becoming a better chemist. Thank you, and any questions?